All right, what's going on, smart people? Last video. So in the previous videos, we showed that for any function f living in sigma sub x, the special simple functions with finite measure support, that are statements that the QT norm of TF is going to be less than or equal to this transition from m naught to m1, m naught to 1 minus t, m1 to the t, times the norm of f, p sub t. Again, in this particular one, this is still from the trivial case, so here p was our pt, but that's pt. We've shown that it's true for all f in this sigma sub x. So what we need to show now is that it holds for all the f in our t mu. So what we're going to do here is we're going to pick a function in that space, and we're going to take a sequence of functions in sigma sub x such that their magnitude is less than f, and such that it's approaching f points. So we then can define the e when the magnitude of f is greater than 1. So all the x where the magnitude of x is greater than 1. And then we're going to split f into two separate functions, h and g. G is going to be defined as f times the characteristic function of e, and h is going to be f minus g. Here, this would be the characteristic function of the complement of e. Then we can define the sequences in the same manner. So there's mistake number 1. There will be plenty, I promise. And so we then can define the g sub n sequence and the h sub n sequence using the fn's now. So moving on to the proof, what we got is we're going to say let p naught be less than p1. And we can do this arbitrarily because just by switching up the variables. One of them has to be greater because, again, our trivial case, we assume them equal, so we know that these are in fact not equal. Then we can say that g lives in LP naught and h lives in LP1. And the reason that we can do this is because g is the smaller part of the function. So when I have a smaller exponent, it's going to live in that, it's going to live in the space where the smaller exponent is taken inside of the integral. And g is the larger part of the function. So when it has a smaller exponent inside the integral, it's going to definitely, if f was integrable in LPT, and LPT is larger than L naught, since g is the large part of f, we know that it's going to live in the lower LP space, and same thing, h is the small part of f. So if f lives in LPT, then h has to live in LP1, where p1 is larger than pt. Now, since our sequence was pointwise, our sequence f sub n was pointwise, we know it's also converging almost everywhere. So we may apply the dominating convergence theorem. So we get three things. First off, fn's are approaching f in LPT, GNs are approaching G in LP naught, and HNs are approaching H in LP1. So what we now get is that T has a complete, since we're in LP spaces, T has a complete domain, and we get that it is bounded, so it is continuous, which allows us to then pass the we know that Cauchy sequences can, these guys are converging, so we know that they are, we can pass them through our linear operator, our continuous linear operator as well. So we also get that they're converging in TGN is also, and THN are also converging. Now, one note that we should make is that because we've already shown that, and I forgot to bring this up at the beginning, but because we have already shown that the function, that our theorem is true for a function that's dense in LPT, also get that there exists a unique extension to all of LPT, satisfying our estimate. So what we're doing now is just showing that, in fact, T is that extension. So that's just a point of, just a technical point that I forgot to bring up at the beginning of the proof. So now that we are here, we have, we can use a generalization of proposition 2.32, which allows us to take a subsequence of GN and the HNs and say that they're converging almost everywhere. Because if we remember, proposition 2.32 gives us, one moment, 2.32 gives us that if Fn is approaching F in L1, then it is approaching, then there exists a subsequence that's approaching almost everywhere. So we use the generalization of that theorem to give us that they're approaching almost everywhere in these cases. And then we have that TGN sub L is approaching TG, and TGH sub NL is approaching TH almost everywhere. And what we're going to note here is that it guarantees that a subsequence of each exists. So what we're going to do is take the subsequence where they overlap, and we then we only need to use one index. Now, because the indices are the same, we can sum them and get that TFNL is approaching TF almost everywhere. So now that we have this, we are almost done. So last board visible? Yes? Okay, good. So now, since we are working within an LP space, the first thing that you do when you take an LP norm is you take the absolute value of the function. And since the FNs were chosen to be smaller in magnitude than F, we can replace this TFNL with the absolute value of TFNL without affecting the bounding constants of T. What I mean by the bounding constants of T is these M naughts and M ones. So we can replace it there. And the reason that we want to replace that with its absolute value is that it allows us to apply Fato's theorem, Fato's lemma, which says that we can pass the limit through an integral. And by doing that, what we get is that TF is going to be equal to because we have that it's approaching almost everywhere from below, we can take the lim_inf of T, we can replace TF with the lim_inf of TFN, and then we can pull the lim_inf outside of our norm. Then, because we have already shown for the FNs that they are bounded in the, these should be Qs. Sorry. These should be Qs. Then, since the TFNs live in the sequence of X, we've already shown that we can that it's bounded above by the M naught to the 1 minus T, M1 to the T times Fn PT, and then we can apply Fato's lemma again and move the lim_inf back inside and replace it. So then we have the lim_inf of Fn, which we know is going to F. So now we have that our function, that the image of F in the QT norm is in fact bounded by our product of the powers of the bounding constants and the PT norm of F, which gives us the theorem as desired, since F was chosen arbitrarily in LPT. So Muerto al pollo. Okay, sounds good. I will see you guys next time.